Okay, clean sheet of paper, time to do something new. And what we're going to do is not look at that. We're going to look at something else. All right, so we're going to look at a problem here. I'm taking these problems, by the way, out of your textbook. They're not overly complicated. So we're going to have to do a little math, but it's okay. The idea is that we're going to describe the motion of something. And when we talk about circular motion, it just has to be at that moment in a bit of a circle. It doesn't have to be all the way around the circle once. So what we're going to describe is a train that takes a circular bend. And we can describe the radius of this, right? So in red here, I want to put in that there is a circle here. And the radius of this turn is going to be 173 meters. Yeah. Trains need a nice slow curve like this. So this is one of those fast trains, and what it's doing is, so we draw in a train, and then there's more train behind it. This train's going in, and its speed at the start of the turn is 83.4 kilometers per hour. And at the exit of the turn is speed, so this is V initial. We'll have V final is 55 kilometers an hour. And so what we want to do is find the acceleration when it reaches this point. All right, we want to find the total acceleration as it's getting to this speed. Now, what's going to happen is it's probably going to continue going around. Maybe this point is actually up here somewhere, and it continues on. So at this point, we want the acceleration here, and that's the total acceleration. So remember that the acceleration looks like the radial acceleration plus the tangential acceleration. And we're doing that because when we have things in a circle, something that's moving in the x direction will eventually be moving in the y direction. So we want to make things in terms of the circle. Right? So we can go in with a nice purple color, and we'll say that this is our radial direction, and this is our tangential direction. And this seems unusual, because what's happening is these things change. They actually vary with time. They rotate around. At some point, this could be our radial direction. But the orientation should be the same, so the tangential direction should be the same as well. Right? So the directions can change, but they're all in reference to this circle. So there's some part that is into the circle, and then some part that's tangential. So we have those, and that's pretty good. We do need to figure out what these velocities are in like normal units for us, and so we'll do that. Our unit conversion here we're going to do in pink. All right, we'll do 83.4 kilometers per hour. Right. And then we're going to do times 1 hour is how many seconds? 3,600 seconds. You can do 1 hour is 60 minutes and 1 minute is 60 seconds. Or you can know this is true, and that's fine. And then we need to do 1,000 meters per kilometer. And the idea is that, kilometers up here, so you got to have it cancel out. It's in the bottom. Hours are down here, so you got to have hours up there, and that's how you know how to do that. And so what this means is you're dividing by 3.6. We'll do it all the way through 83.4 times 1,000 divided by 3,600 And this is 23.2 meters per second. So we'll put that in. And we'll do the same thing down here. And what we get is that this is 15.3 meters per second. Okay. So we've got that. That's real good. Now, the tangential acceleration we can do as if everything was in a nice straight line. All right, we can treat this is the stuff that is 1D motion. And this is the stuff that's circular motion. All right, this is the part that makes the thing turn, so it's in the circular motion. This is the bit that makes it speed up and slow down, so it's 1D. So when we do that, what we want to do for the tangential acceleration, well, we don't know what delta x is, because it could be a significant portion of this curve. It's not described. We also need the time, and I constantly do this. Is it the problem actually exists, and I'm reading it, and I missed the time. We'll say that this takes 12.5 seconds to go around this curve, because it's a big curve. So delta x is something. V initial is 23.2 meters a second. V final is 15.3 meters a second. The acceleration is unknown, and the time is 12.5 meters per second. And so if we have that, then we can go and say, oh, well, I have my velocities and my time. I can get the acceleration just from the definition. It's delta V over t. And so delta t is V final minus V initial, so 15.3 meters per second minus 23.2 meters a second divided over 12.5 meters per second. So that's my acceleration, the tangential acceleration. And then we can solve what that is. And that is 15.3 minus 23.2 divided by 12.5. That is minus 0.632 meters per second squared. Now, for the radial bit, we have to apply our circular motion for that. Right, so we come down here and say, well, in the radial direction, actually, let's just get new paper for this. So slide a sheet off to the side here. Right. So in our radial direction, we have to take from our information here that we have a curve and we have some velocity that we care about. So when we organize our information, it's going to be, right, our radius is 173 meters and our velocity is 15.3 meters per second. And now we're trying to get the radial velocity out of that. But what that equals is v squared over r. So we can just calculate it. There's our v squared divided by r. And so we check that'll be squared, cancels, so we'll get an acceleration. Okay. And so 15.3 squared divided by 173, and we get 1.35 meters per second squared. Okay. Yeah, there we go. Running out of screen on the display. So now what we're going to do is draw a picture again of, right, so there's my circle. But what's happening is at some particular instant in it, I have this radial acceleration, which is 1.35 meters per second squared, and it looks like that. But then I also have a tangential acceleration. And this is my minus 0. So it's in the wrong direction. Put it up here. Minus 0.632 meters per second squared. All right, so we have one vector that looks like this, and I can shift this over. It doesn't matter. I can just pull it over here. So this is our minus 0.632. And so when we get this, we'll get an acceleration, and the negative means that it's going behind the train. It's pulling the train, slowing it down. So we're not going to worry too much about the signs here. We're just going to go in and say, well, maybe, the negative is telling us about the direction if it shows up. But we know that the train's slowing down. We need to get this angle theta, which is how this acceleration vector points behind the train. And we need to get this acceleration. And the acceleration's easy enough. Our acceleration looks like the square root of the radial acceleration squared plus the tangential acceleration squared, and then we just calculate it. All right, so we just write everything out. Okay. And then we sit and calculate it. That squared plus 632 squared, and we get a number, and then we take a square root. And this is 1.49 meters per second squared. That makes sense. It's larger than our components. We're trying to find a hypotenuse. That's what we want. That's good. And then finally, we got to get this angle, and the angle comes from tangent theta is opposite over adjacent is, in this case, it is tangential acceleration over the radial acceleration. And so we can find that theta is inverse tan, and then we can put in 1.3, nope, that's not right, 0.632 meters per second squared with a minus sign over 1.35 meters per second squared. And so if we do that, 0.632 divided by 1.35, an inverse tangent, this is minus 25.1 degrees. And looking at my solutions, I trust that that's right. But the minus sign is telling us it points backwards. All right, that kind of makes sense. The train is going this way around the curve. My acceleration is that way. So yeah, it's got a component backwards. That makes sense. These are all reasonable numbers, right? If you've been on a train, you don't feel like you're falling. It's going around the curve and it's slow. So that makes sense. And a lot of this is just vector stuff. But whatever it is, I promise you that it is those equations and the stuff you've already seen. Right? Is if something is speeding up, then you go and you do the one-dimensional motion that you've already done before. For the bit where it actually speeds up or slows down, you do this. And for the bit where it turns, you do this. And you have everything you need. So that's this video. And I think that's basically the kind of problems you have. So this is where you go off and you try the homework, and then you let me know if there's anything else that you need out of this, and we'll converse on that.